bigger. All right, so chapter 5, 6, and 7, we don't do all of them. Like chapter 5 is 5 sections, we're only doing 4 of them, and then chapter 6 and 7, we're only doing 2 sections from each. But those 3 chapters, 5, 6, and 7, what we do of them is going to make up your next test. So next couple weeks will be chapter 5 stuff. Today, we're just going to start talking about normal distributions and a normal curve. So this is the first set of information you guys have on your little handout there. So you can use that to get a couple of your definitions down if you want. So a normal distribution is a continuous probability distribution. So we did probability distributions in the last chapter. If we start graphing them for our normal variable x and we get a shape that looks something like this, like in a histogram or something, we call it a normal curve. Bless you. Sometimes it's also called a bell-shaped curve. And you can see why it would get its name. So there are some properties listed here about our normal distribution and our normal curve. Number 1, your mean, median, and mode. Oops, maybe if I can get my pen there. Are all the same, and they're all where that mean is in the picture, right in the middle. It's your line of symmetry. It is bell-shaped and it is symmetric about the mean. Okay, so you're going to see symmetry always where that line is. The total area under the curve is going to be equal to 1. So think of this almost like a probability distribution. Probability distribution, all of our probabilities added up to 1. So if we, start graphing something like that, and it looks like this, our total area underneath would be the total probabilities, which would equal 1. So all these pieces are going to start coming together now. And then just like back in like college algebra, when you talked about asymptotes and things, our bell curve does not ever actually touch the axes. It just gets really, really close to the axes on either side. Okay. So I'll let you summarize that on your definition sheet however you want. Okay, the next slide on your paper has to do with inflection points. So now let's say we've got this normal distribution and we put in our mean and now our standard deviation. So we've seen this picture before. You guys remember with the empirical rule with like the 68% are within 1 standard deviation, the 95% are within 2 standard deviations. Well, if I take a line up from my standard deviation, that's 1 away from my mean, we get these points called inflection points. Inflection points can be found first and then help us actually find the standard deviation. We're going to approximate these the best we can for right now. We'll eventually be able to calculate the standard deviation, so we won't have to estimate off of the graph. Let's say we'll be estimating off the graph. These points are where the curve changes from concave up to concave down. So if you haven't heard those terms before, concave up is almost like a parabola that's opening up. It's what that shape is. And then concave down is a parabola opening down. So if you look on this left side of the bell curve, this left side is what we say is concave up. It could be maybe part of a parabola, or even maybe it looks like part of an exponential function. And then at that point, it kind of turns around and becomes almost like the top of it is a parabola opening down. So that point is where it's changing from concave up to concave down. It's approximately, kind of, sort of, in the middle of the side of the hill. Again, do the best you can to estimate it at this point. All right, if we have a distribution that is not symmetric, so it's not going to be this bell shape, but it does have an area of 1 and it doesn't ever become negative, it doesn't ever go below the axes, we call it a probability density function, or a PDF. You might see that word used sometimes interchangeably with some things we're doing, like the command we're going to use in the calculator is a PDF. It works for normal curves and other types of curves as well. All right, so things we're going to do with this. We're first going to take these normal curves, normal distributions, and we're going to answer questions about the mean and the standard deviation. So for right now, we are just approximating based on the picture. We're doing the best we can. Now, the means are all drawn in here for you. They've got the little dashed line right down the middle where that line of symmetry is. So can you tell me for graph A what the mean is? 3.5. What's the mean for graph B in the middle? Also 3.5. And the mean for chart C there? 1.5. Good. Okay, now if I want the standard deviation, we're going to use those inflection points. Take your inflection points, and they've drawn them in here for you, and drop them down to the axes. Your standard deviation is going to be the distance between the mean and one of those lines that we've got from the inflection point. You can either look to the left or to the right. They should be the same. So if I look to the right, for example, it would be the distance between 3.5 and 5, which would be 1 and 1.5 would be my standard deviation. And it should be the same if you look to the left. If I look to the left, it goes between 2 and 3.5, which again, that difference is 1.5. All right, so what would you estimate the standard deviation of the one in the middle is then? Standard deviation is going to be 1. If you drop those inflection points down, they're about 1 unit from the mean. And then what about the last one? Also 1. Okay. Questions on that? Great. Okay, let's look at this picture. Quick question. Can you tell me which normal curve has a greater mean? A or B? Why? How do you know the mean is greater in A? Because it's taller? Why?
Because the middle is farther to the right.
Yeah, the middle line, your line of symmetry is where your mean is, and it just happens to be further to the right here. So we would see B has lower mean. Make sense? And then standard deviation, which one has a greater standard deviation? B. Why? More stretched out. It's more spread. Yeah. Good. Okay. Let's look at this problem. So it says the scale test scores for New York State grade 4 Common Core math test are normally distributed. The normal curve shown below represents this distribution. What is the mean test score? And then estimate the standard deviation. Okay, so they don't have any lines drawn in here for you. So again, you need to approximate off of the picture. So find your line of symmetry. Top of the hill. Drop it down. Looks like it's falling between 2 tick marks on mine. Can you tell me what you think that is? $305 would work. Somewhere between 300 and 310. Okay, and then standard deviation. We're going to try to find that inflection point. Again, imagine following the curve, and we want to know when it's changing from curving upward to curving downward. And that's where our inflection point is. So, I mean, I think that's going up, and then maybe right there-ish. It starts to then turn around and go curve down. So maybe like there, maybe. Something like that. Again, it should be symmetric. So approximately the same location on the other one. Now where I have it drawn, again, it looks like it's falling between a couple tick marks there. Like mine looks like it's hitting at between 340 and 350. So I'm going to say 345. This one looks like it's between 260 and 270. So I'll say 265. So either way, my standard deviation then, that distance, would be about 40. Again, that's a approximation. Okay. All right, try the next set of questions on the bottom left slide on your paper. Those should be, again, some quick little practice with this. Mean, standard standard deviation from our normal curves? Okay. Once you have them, check your answers with your group. Compare. See how you did. Okay. All right, number one, which one has the greater mean? B. Which one has the greater standard deviation? C. Perfect. What did you estimate the mean to be? 3,300. And then standard deviation, approximately, I would say 600 sounds good. Great. Any questions on those? All right, last slide you need your graphing calculator for. We don't do this too often, but it's just kind of an interesting thing you can do in your calculator. You can graph a bell-shaped curve in your calculator. So let me show you how to get this. We're going to go into y equals. I had a few people in first period that had r's here instead of y's. Does everybody have a y? We're okay? All right. Your plot does not need to be on. I don't know why it says that on the top there, so leave your plot off. Okay, to get normal PDF, probability density function, remember I said you were going to see that. That's in the distribution menu, which is above the word vars. It's on that button. Okay, so we're going to hit second vars and then select normal PDF. Now, if you have the newer version of the calculator, which I'm guessing most of you do, it'll look like this. If not, you're just going to have to type the commas in with the information between them. Okay, so this one, we're going to use an x value of just x, so use your variable button there. And then our mean is going to be 305. And then our standard deviation is 40. In the older calculator, you just got to remember it's variable, mean, standard deviation. And then you can hit paste. Oops, I disappeared. And it should go into your y equals. Now, this calculator wasn't doing it, but my calculator on my desk was. If you hit zoom fit, it might graph it for you. My calculator doesn't love this so much. Does anybody see a bell curve with zoom fit on theirs? Yes? You see the whole bell curve? Okay, if you don't see the whole bell curve like mine up here, if you go to window, you can adjust this a little bit. You can make, remember your x is how far left and right it's going to go. Now this problem has a mean of 305 and a standard deviation of 40. So I'm going to make my x min like, I don't know, 150. And I'll make my x max 500. I'll go a little bit in either direction. X scale, you can leave it as 1 or you could change it to like 50. That's just how often you're going to see a tick mark. So probability density functions are not going to go below 0. So my y min is going to be 0. And the whole area underneath the curve is 1. So these aren't going to go very high. They're going to actually be very small. So you could put like 0.01 for your y max. 0.01 would work. And then graph it. And then you could always adjust a little more from there, but you should see this shape on there in some way, shape or form. Okay. Put that on there. Everybody able to get that okay? Okay. And you could always change, you know, the window based on what your mean and your standard deviation are if you needed to. But zoom fit worked for the most part. Yours isn't doing it. syntax error. Go to. There. That. Okay, so it's just parentheses, X, that, and that. Okay. Everybody else? Show up okay? All right, that is the end of the lesson today. We are done. So I'll do the cell phone lotto. You can use this class period how you like, but remember, no homework this weekend.